Good morning, everyone. Myself, Assistant Professor Sandeep Shah, working at Technocrats Group of Institute Bhopal. So, we are going to start a new chapter, that is thermal radiation. So, these are the table of content of heat transfer subject of chapter thermal radiation. That is the radiation. First one is the introduction of radiation heat transfer. Second is the concept of thermal radiation, and then we will study about the governing laws of radiation heat transfer, and then further we will study about the relationship between absorptivity alpha and emissivity epsilon, and next is the view factors integral method, and another one is the electrical analogy of radiation heat transfer. So first we will understand what is the radiation. So radiation is the energy transfer across a system boundary due to a temperature delta T, temperature difference delta T, by the mechanism of photon emission or electromagnetic wave emission. So we know that any surface is having at a temperature, given temperature will always emit some amount of radiation, and this radiation, due to this radiation, the heat transfer takes place. So what is the electromagnetic phenomena which is responsible for radiation heat transfer, we will understand. So you can observe here that this is the wavelength spectrum of different electromagnetic waves. Depending on the wavelength, we can categorize different ways. So our study will focus over this range, that is 10 to the power minus 1 to 10 to the power 2, that is light waves. So here thermal radiation will be taking place due to thermal radiation. So electromagnetic phenomena we can understand. We are well acquainted with a wide range of electromagnetic phenomena in modern life. These phenomena are sometimes thought of as wave phenomena and are constantly often described in terms of electromagnetic wavelength lambda. So the laws which is responsible for the convection heat transfer is the Stefan-Boltzmann law, and it is given by EB is equals to sigma TABS to power 4. It means the EB is the emissive power which is directly proportional to the temperature to power 4. So the gross energy emitted from an ideal surface per unit area is known as emissive power, and the sigma is the Stefan-Boltzmann constant, and its value is 5.67 into 10 to the power minus 8, and TABS is the absolute temperature of emitting surface in Kelvin. Another law is the Planck's law, that is if emissive power of a body depends on the wavelength, which will be the function of lambda. So while the Stefan-Boltzmann law is essential for studying overall energy emission, it does not allow us to treat those interactions which deal specifically with wavelength lambda. So here emission which is depends on the wavelength lambda, this phenomena is overcome by modern physics, that is Max Planck, who developed a relationship for wave-based emission. So another one is the term or law governing to the heat transfer, that is monochromatic emissive power. Monochromatic emissive power, and it is given by EV lambda, and it is an implicit definition is provided by the following equation. So monochromatic emissive power will be given by EB is equals to 0 to power infinity EV lambda d lambda. This is a graph which is showing the area EV. It means by integrating the whole area will define the amount of heat transfer. A definition of monochromatic emissive power would be obtained by differentiating the integral equation. If we will differentiate this integral equation, we are getting a definition of emissive power. Here EB lambda is equal to C1 upon lambda to power 5, and e to power C2 upon lambda T minus 1. Here C1 is a constant, C2 is also a constant. The actual form of Planck's law is given by this. So these all are the parameters, constant parameter, and value of constant is also given. Now the surface properties, we know that the emission is a radiation emitted from any surface. So emission, we must know about the surface property or the nature of surface through which the radiations are emitting. The first one is the real surface. Real surface means the energy emitted from surface according to Stephen Boltzmann law is EB is equals to sigma T absolute power 4. Here real surface has emissive power E, and which are somewhat less than that obtained theoretically by Boltzmann. So to account for this reduction, we introduce emissivity epsilon. So emissivity epsilon is E upon EB. E is for a real surface and EB is for black surface. So the emissive power from any real surface given by E is equals to epsilon EB. Now this was for the emission. Now next is for receiving property, because any surface, the surface which will emit radiation will be received by another surface. So we have to also study the properties of receiving surface. The first one is absorptivity. First one is absorptivity. Receiving property, absorptivity alpha, and reflectivity rho, and another one is okay. So absorptivity is the fraction of incident radiation absorbed, and reflectivity rho is the fraction of incident radiation reflected. So there is a conservation of energy. Alpha plus rho plus tau is equals to 1. Tau is the transmissibility radiation transmitted from the surface. Now the relationship between absorptivity alpha and emissivity epsilon. So here we can see that this is the surface where incidence of radiation is taking place, and some amount of radiation are reflected, and some amount of radiations are getting transmitted. So the relationship between alpha, absorptivity, emissivity and transmissibility is given here. We can say that by considering two flat infinite plate surface A and surface B, both emitting radiation towards one another. Surface B is assumed to be an ideal emitter, that is epsilon B is equals to 1. Surface A will emit radiation according to Stephen Boltzmann law. So now if we will discuss about the absorptivity and emissivity relation. So for this surface, the absorptivity of surface A will be equal to emissivity of A. Now the relationship between emissive power and intensity. So the definition of two terms, emissive power for an ideal surface EB and intensity for an ideal surface IB, is given by emissive power EB is equals to pi IB. So to express the total energy emitted from surface 1, we recall the relation between emissive power E and intensity I. So the Q energy or heat emitted, radiation emitted Q is equals to E1 A1 is equals to pi I1 A1. So this is the formula to calculate the heat radiation emitted. Now the next term is the view factor by using integral method. So define the view factor F12 as the fraction of energy emitted from surface 1 which directly strikes surface 2. So the view factor may be defined as the fraction of radiation energy emitted from surface 1 and directly striking surface 2. So the next term is the reciprocity. So if we are having two surfaces, one is emitting and another is receiving, so the formula to find out or calculate fraction of energy or radiation striking to surface 2 will be using reciprocity theorem. So this is the integral form of reciprocity theorem, reciprocity formula. So we are having finally, if let us suppose that we are having two surface, that is A1, surface area A1, or view factor F I to J, another surface is J. So the view factor with respect to I is to the J is Fij, and another one will be Aj, and view factor of j with respect to I. So the product of A and F will be equal from I to j and j to I. So this is known as reciprocity principle. Now the next law is the rule, or law is associative rule. So let us suppose that we are having the more than two surfaces. So to find out the view factor, we will use, or we will integrate with by considering a set of surface, shown to the right. Clearly from the conservation of energy, the fraction of energy leaving surface I and striking the combined surface j and k will equal to the fraction of energy emitted from I and striking j plus the fraction leaving surface I and striking k. The next term is the radiosity. Radiosity J is defined as the total energy leaving a surface per unit area and per unit time. Now the next term is the net exchange between surfaces. So let us suppose that the surface 1 is also emitting radiation, and another second surface is also emitting some radiation. So what amount of energy will be, net energy will be emitted? So we can calculate by using this formula. The net energy leaving a surface. So the net energy leaving a surface will be calculated by using this formula, that is J equal to epsilon EB plus rho G. So this is also a final formula to calculate the net radiation emitted from any surface, is that is Q1 is equals to epsilon A1 upon 1 minus epsilon EB minus J. So the next term is the electrical analogy for radiation. So we know that as in case of radiation heat transfer, we are having a temperature difference similar to a potential difference in case of electrical circuit. So here we are having equivalent current, here resistance R, here potential difference delta V. So by using the Ohm's law, we know that if a voltage difference is between the two terminals, so the current flow will take place. Similarly, if there is temperature difference between two surfaces, then the flow of heat will take place. So the net energy leaving surface is Q1, and the equivalent resistance will be given by 1 minus epsilon upon epsilon A, and potential difference EB minus J, and net exchange between surfaces Qi to J, and here resistance 1 upon A1 F 1 upon 1 to 2, and potential difference J1 minus J2.